Good morning, everyone. I'm Alex. Thank you for coming. It's very heartwarming for me to see that so many people decided to come up at 9 a.m. It's also a bit scary because, as I was telling the gentleman in front, I was counting on roughly 5 people, maybe 10. So there's quite a bit more pressure now with a wide audience. You've also spread out so that I have my work cut out for it. I'll go over there, go over there. But hopefully it will be fine. I used to be, and I will be again, software engineer in the graphics business working for an IHV. My prior employer used to be Imagination Technologies, if you know the dudes. They do the IP for the iPhone, iPad, and so on and so forth. And as you can imagine, it was pretty important for them being in the handheld world to work on Vulkan. Therefore, my task for most of my time there was to work on Vulkan. Now, I must make you aware of 2 things. This is not intended to be a talk in which someone comes with the truth and imparts it, and it's not one of those moments. I mean, I am Romanian, I'm not Andrei Alexandrescu, so I'm just a programmer like you. If you feel like asking questions throughout the talk, do. I don't guarantee that I always have answers, but I might know where to look if I don't have an answer. And having said that, let's look at the wonderful discovery of the lack of 0 in Roman numerals. This is what we're sort of aspiring to. Now, given my experience with prior talks that I've given and my pace, I don't know if we'll make it up to the bottom, but we have a fair chance to make it up to the graphics point. So the goal is to come up from very high level with an abstraction that sort of starts from first principles of rendering and of computation more than it starts from I have an API, I have to wrap it into something. There are a bunch of other tools that do the wrapping for you. If you want to use them, they're great and very useful. For example, Kronos just adopted an .hpp header, which was contributed by NVIDIA and has a bunch of nice binding and strongly typed enums and all of that good stuff. This talk is not about that. It's more about, as you'll soon hear, being thrust into the front line and trying to make heads or tails coming from a slightly different background. So as I said, I joined Imagination about 1 year ago, something like that. And I was coming from a different background, which was GPU compute. And after GPU compute, a bit of MFC compute. If you don't know what that is, you're a very happy man. And I was part of a competitive analysis team. And competitive analysis teams write lots of benchmarks. You can imagine that there's lots of excitement around a new API. So writing a new benchmark for Vulkan should have been very cool. Only that, you have the new guy who's coming from MFC compute and all that stuff. I don't know, write some Vulkan. So my goal in life at the moment, at that particular moment, was to render 2 triangles. Why 2 triangles? That's a good answer. That's a good start. So it's progress. Yes. Yeah, that's a good point. That's very smart, but I wasn't that smart. I'm not that smart. It's something simple. I mean, yes. So if you write benchmarks, the full screen quad is one of your best friends because you can do lots of magical things. I mean, and I see people around and they're looking, wow, you have such a sad life, like a full screen quad. But, well, it's pretty important, you know? You want to measure fill rate, you want to measure the throughput for a particular shader, maybe you want to tessellate it and you want to have it projected orthogonally to the screen. There are some benefits. So I wanted to render 2 triangles. So what do? Well, the SDK sort of thing came out by Luna G, by the way. There will be a link later on. So I go in, they have a sample with a triangle. It's an advanced sample, so it's a color triangle and it draws doot and it's animated. But I thought, well, okay, I won't do the complicated stuff. I'll just figure out how to render a triangle and then maybe I'll duplicate that code and render 2 triangles. And maybe if I get really smart, I discover iteration and I don't need to duplicate it. And that was a bit daunting because if you look at, does anybody know the SDK samples? Show of hands? They might be not necessarily newbie friendly unless by newbie friendliness it is understood that you will copy this thing and use it as we use it forever. And don't necessarily try to understand it. It's kind of lots of inline stuff, and you have all of these things that look as if they could be RAII, but for some reason they're not. And you have safe release and all kinds of nice things. So around the same point, I got the chance to interact with some of the people that worked on the API, and also to see one of the demos that they had requested. And one of the main requests in the demo, so that you understand why I was not that was not a good day, was there shall be no abstraction. We don't want any sort of abstraction rubbish we have this low level. We want to expose it, so do everything in line. So if you can. You have one function, okay, fill it up. Do your stuff here. You want create all of your buffers. Compile your shaders with some Python script at the and ask, well, guys, maybe it's a bit difficult for a demo to help me out here. No, it's a very good demo. It shows exactly what you need to initialize and what you need to do. And I couldn't disagree with that. It's just that I probably was not on the level to capture it. So I'm an 80-20 sort of guy. If you go to the 80%, you're probably in a good spot. So I decided to start from the bottom. I figure how the rendering goes. Maybe I'll know how to render 2 triangles. I managed to learn how to render 20. An icosahedron, yes. So this is basically what I wanted to do. That guy up there. So I probably return something. I have a function that hopefully does not have the name foo, because everybody names something foo and you can grab for it. And I have some description of the sort of work that I want to do, and I give it to the function, and magically things happen. Maybe pixels show up, maybe numbers get spit out in a buffer or something like that. Now, another part of my background is that I come from C++ AMP. So does anybody know C++ AMP? Well, you're cheating. Does anybody who is not at Microsoft? No. Well, anyways, certain concepts and ideas and names are shared because I think that was a very good way to program, including for graphics. At any rate, we just want this foo guy. And let us think at what happens in rendering. So in a certain case, you might want an immediate result. So you might want to really block. It might be fine to return like void. You're in an application that might be concerned with its real-time responsiveness, let's say. You don't want to build a long queue that will at some point get split into the machine, and then you have a bump in latency as it chugs, because preemption on GPUs is still tricky. So that's fine, but in other cases, you might want some sort of composability. And we'll see that it's even more relevant in the context of Vulkan once you start submitting against multiple queues, all in due time. So maybe a future void. Does anybody have anything against the future void? No? By the way, questions? No? Very good. Now, in order to what sort of workloads do you have in graphics? By the way, how many graphics programmers? Okay. GPU compute people? Okay. How many Vulkan programmers? Do I need, well, later on, if I need to detail certain things about Vulkan, do give me a shout. Anyways, so let's assume that we live in this simplified universe in which you either need to do compute, where compute is defined as some transformation that does not necessarily yield a visual output. So multiplying matrices or adding vectors, all of these super exciting things. Or you're doing graphics. So you're rendering Doom. Maybe not Doom, but maybe a part of Doom, maybe a part of a Doom scene. So this is not bad. And with all computation, everything in computers, and it's sort of two-sided. So on one hand, we have bits that kind of travel, but they don't really travel. And we modify them, and we get new bits. And describing the pipeline thing and the workload thing we modifying the bits. But we need to hold them somewhere. We don't really hold them, but anyway. So containers are good. And there are two concepts that buffer is general. It's probably one of the most general concepts in compute. Typical container. Texture is a bit more special case to graphics, but it is a special case of a buffer, and we'll approach it from that angle later on. So I'm pretty bad at naming. You'll have to apologize that. But run pipeline might be okay, because the machine itself is a pipeline, and you'll see everyone talking about the rendering pipeline. Everybody knows what the rendering pipeline is made up of. Now, in terms of design, we'll get back to the rendering pipeline and it will make sense. In terms of design, there are a few things that I hold to, and I hold to them as a C++ programmer and a programmer in general, and I generally get slack from people for this, but I think that they're pretty important to have, especially in the concurrent parallel world. So does everybody know what a regular type is? Okay, let's go the other way. Does anybody not know what regular type is? So a regular type is a type that provides in its computational basis default construction, copy construction, assignment, destructor, equality comparison against equality, and that's where it stops. The totally ordered guy that you see there adds default ordering with the less than. And why would totally ordered be useful? What does it enable?
You can sort them.
Yeah, and after you sort them?
They stay sorted in the same way.
Yes, and with this, I can do log search. Sure. That's probably the more useful, one of the more useful consequences of it. Semi-regular loses the equality comparison because in certain cases it's really hard to compare things. For example, comparing functions. And we'll see in the thing that we build a point in which actually it's very hard to come up with viable equality. These might seem like spurious concerns, like why do you care? And regularity also means another important property of regularity is that you have value semantics for your types. And what it means in a parallel sort of concurrent world is that if you give me a buffer thing against a particular, it's my buffer. I know that I'm not going to cut the legs under somebody else somewhere else. So, and if you give me a reference to it, I'll know to be careful because somebody else might see it. But once you have all of the good stuff that Sean Parent hates on, once that happens, once you perfect regularity, it's very hard when you're in a parallel context. Even more so, as we'll see on a GPU. Now, since there weren't so many Vulkan people, this slide actually makes sense. I was worried that everybody will be, I know this. Vulkan is intended to be a low-level API, a low-level abstraction on top of accelerators, machines that can accelerate parallel computation and graphics rendering. It just so happens that right now that means GPUs, but you could think hypothetically about a scenario in which someone produces a software rasterizer for Vulkan, and it would still qualify as a VK physical device, even though it's not necessarily a VK physical device. It would be enumerated by the API. So the API takes all of these and shows them to you. Look, this is what you can use. This is what I can give you. All of the compliant implementations. And in order to query this stuff, you have to go through an instance. The instance is your gateway into the hardware resources. So I already managed to kill 2 people. That's pretty good. It's your gateway into this world of physical things. The physical things are immutable for all intents and purposes. So if you suddenly get you have to understand that a big part of the things that the Vulkan API exposes happens to be relatively opaque handles or pointers into structures that exist within somebody's driver. So if you actually knew what to cast the pointer to, for example, for a VK physical device or for some other handles that Vulkan returns, you could stare into somebody's driver and see a bunch of, in some sense, you can observe the convergence between the drivers that IHVs came up with. At any rate, as I was saying, if your VK physical device sort of disappears, probably your machine exploded. So you're already in a bad spot. You can take these as being immutable. The instance, however, is not immutable. You grab it and you release it at some point. But since it's sort of the gateway into some things that are immutable, it's a pretty good candidate for being made both static and also probably const after you created it. And you just talk to it like, well, this GPU guy, tell me something about it. I would like to find out something about it. When one creates this gateway, there are a bunch of knobs that are useful, especially for someone who begins programming, because certain errors can be a bit daunting. It's a rather verbose API. Has anybody written drivers here? Drivers. It's verbose. You have many structures, you have many things to set, and now you get, as a non-driver programmer, get a bit of exposure to that. So one of the things that you can enable through an instance is a bunch of validation layers, which basically look at, for example, the arguments that you pass to a particular Vulkan function, and they tell you, no, this will never work, you're wrong. And they spit it out into a nice CR or whatever, into a log file, wherever you want to put it. It's useful to enable them, and versus the initial situation in which it was a bit of the Wild West, now there's just a single sort of meta layer that activates all the validation layers. We'll see it activated later on. Extensions are more of a gray area. There is a set of extensions that is useful. The ones that concern themselves with interaction with the windowing system, in particular. So by way of these extensions, you can theoretically go Linux, Windows, wherever, and it will abstract away some of the difficulties of interacting with the windowing system, because when you do rendering, you do need to retrieve handles to the window, to give handles, to be able to render into it, to log the back buffer, and so on. There are other extensions that might be more pernicious, that tend to be potentially IHV specific, but those tend to be associated with devices more than anything. Since I was talking about immutability, this is sort of how I propose that you start a Vulkan app. Like you grab your instance, you create it. Now, you'll see a bunch of things that are prefixed with info. These are relatively fatty structures that describe the sort of thing that you want to retrieve from the Vulkan runtime itself. And they have a standard form. They are prefixed with the type, because this is kind of C, so you look at the type tag and you know the size. They have a bunch of hooks for custom extensions and so on. More often than not, this is boilerplate that can be automated, and the knobs that you have to twist are quite limited. So in this case, for example, in the VK instance create info, what you'd actually care about modifying or would ever modify is the extensions and the layers that you enable. In this particular case, for debug, the validation layers are enabled because it's noisy and potentially a performance cost, but as for release, they are not enabled. Similarly, for this particular code that will go up probably after the presentation for a while, not for long. For this particular code, I sort of punted the issue of which extensions are good and which aren't, and I just enable all of them. There is a mechanism to retrieve the extensions from the instance itself. If you see, I have a pointer. I don't think it will. Can you see anything with the pointer? No. Well, anyways, if you look upstairs, there's a function called extensions, and there are a bunch of useful helpers that you will discover that you can write and per use that are basically projection functions. They take and they query a particular quantity that you want to retrieve, and they give it back to you. In this case, extensions gives you back the extensions that are supported by the instance. And interestingly enough, there's also a function names, which is a proper projection function. Why does that exist? Because what you pass into this particular structure and many other structures is arrays of strings, no terminated strings that denote. So for example, the set of extensions that you enable is basically a range of zero terminated strings that tells vk blah blah blah, vk blah blah blah, vk blah blah blah. But what you get via the direct query into the instance is a fattier structure that gives you more information about the layer itself, or the extension itself in this case. And by way of consequence, since I just need the name, take it out, stick it into the proper container. It's going to live throughout the scope of this, and Bob's your uncle. Another thing that you will observe, but this was a common pattern for anybody who did OpenGL or who did DirectX and so on, and all of those terrible safe release macros stem from there. Generally, your interaction with the graphics API is, give me this thing, which happens to be a handle. I'm going to do some things with it, and I'm going to return it to you. And there are quite a few types of handles that you can get, but for whatever reason, there is a bit of an aversion in the community towards doing area II, because some people don't like C++, or anyways, at any rate, this is a basic workhorse kind of thing that I've found to be terribly useful in the interaction with Vulkan. Whenever you get a handle, put it in this sort of handle class, and in its destructor, it handles the release properly. So this, it's boring, every C++ programmer knows it. However, there is a bit of variation here, because symmetry is not nice. There are multiple ways in which you can actually return a handle to the Vulkan runtime. And they sort of depend on who's your daddy. In what regards an instance has no daddy. It is the daddy. Therefore, you can simply call the deleter, whatever that might be, on it. You just get the handle to the instance, which happens to be a pointer. You call the deleter on that, and not std delete, a Vulkan function that gives it back to the runtime, and that's that. However, as we'll see later on, once you start getting things from the instance, for example, a device, which is an actual thing against which you can do work and is a programmatic proxy for all of those VK physical, immutable, lovely things, well, you need to talk to dad and tell him, well, you gave this to me, I'm giving it back to you. So, before we move on and show why that is relevant, does everybody kind of guess what all of this strange private inheritance thing does? Is anybody not guessing and curious about what it does? So the basic, I think that in the literature they call it Barton-Nachman trick for this kind of stuff. So what it does, it automatically, in some sense, by following a convention of a function that you must implement yourself, it puts, for example, the quality and inequality in the adequate namespace. It hoists it outside, and it generates it for you. And the one at the bottom is actually a very boring kind of empty class with the const per constructor, and within the body of the constructor, it static asserts that it actually has the proper properties. So it's default constructible, assignable, and so on. Which is precisely what's listed here, so we can go on. Another convention that's probably useful in your code, you'll discover that you'll have to interface. Even if you wrap these things, you'll interface with the API relatively frequently, so you should be able to retrieve the handle that the API gave to you. And anticipating a bit, you also discover that Vulkan is, not only Vulkan, but is a bit like the sort of drug dealer that wanted to use you as a mule on your vacation and who gets caught, as in, you gave me this thing. Nah, but you gave me this buffer. Tell me something about it. I mean, you know its size, you know. No. By which I'm trying to convey the point that you don't have much introspection back into the API. So you might create a buffer at some point, or you might create a device. There is useful information that you will need later on that you should store with it. And as you go through the hierarchy, it's useful to store back pointers to constant whatever you're born from, because that guy might have some other information that you need. Now, the point of the funky constructor is tied to what I was saying earlier about the deleter. The idea is that it's kind of nice to hoist all of these 10,000 billion functions into one particular point and to have sort of symmetrical deletion. And when you construct a particular, if you construct a Vulkan handle over an instance, you know that it has no daddy. If you construct a device, you know that it has an instance daddy that it might need for its deletion, although the device does not. But when you construct a buffer, you definitely need to give it back to the device that gave you the buffer. It's in the call of the function. So how this works, there's an outer scope, again, kind of empty body sort of struct in which you have just the call operator, which is overloaded based on all of the types that you want to delete. And within the body of is the actual call into the Vulkan API. Some need to call other things. For those that need to call other things, they are able to pass it through the forwarding constructor at construction. So you need a pointer to, you need a handle to the device that you came from. You can give it to that. You need a handle, you can give it to that. And this just, so as I was writing the code, as you start adding types, you discover, well, I need to free this as well. And you do the Vulkan handle and it says, well, I don't have an overload to delete this thing for you. And it's sort of self-filling. Just go add another overload. This is kind of what is enough to do pretty interesting stuff. It was enough for my 2-triangle challenge. But it's actually enough for doing reasonable graphics as well. It's definitely enough for computation. We'll talk about each of them in context. It's not a large set, as you can tell. And there's also the funky function with the run pipeline, but there's not a ton of stuff. This is possibly the most important abstraction in the lot of it. And I pilfered the name from AMP, Accelerator View. And what it maps to into the actual API is a Vulcan device. But the idea is that this is actually your joystick, your joint game controller, whatever, to the resource. It is your view to the particular computation resource. And this is something that you can hand into a thread, and that thread can bang against it and leverage that particular device just fine. And you can hand it to another thread, and that other guy will bang against that device. They will not. This is the thing that enables you to create resources against a device, to submit computation, and so on. You need it everywhere. Just like you need a VK device everywhere, you need this kind of guy everywhere. Does anyone have any issue with the odd requires and the domain thing? No? Good. What do I mean by the domain of f equals void? Come on, guys, help me out. I mean, it's a poor person, it has a void domain. Pardon? Codomain is returned. It takes no arguments, yes. This is slightly freakier syntax than the, well, not freakier, but different syntax from the one that's in the concepts proposal, but I kind of want to compile my stuff with Visual Studio as well, and people who haven't implemented it yet. And what I wanted to focus on here is the implementation of a particular function that gives us a command pool. And it might be useful to figure out what a command pool is before. And you can think of a command pool as sort of a heap from which you can, a special purpose heap that is attached to a particular sort of queue, bit of innuendo. These machines can expose multiple avenues for ingesting work. There is guaranteed to be one large, very generic door in which you can put graphics, compute, whatever. But in general, and for many machines, there are other queues which have potentially less functionality, but have desirable properties if your workload maps to them. So for example, it might be the case that you have a compute queue exposed. If you have a compute shader and this has compute queues, submit it there. It's less overhead and it opens the gateway to potential overlap in execution, but we'll talk about that later. So from these command pools, they get a sort of associated, well, definitely associated with the queue. So if I want to submit a packet, which is a command buffer, against a particular queue, I need to grab it from this command pool. So I go and look, I have this, I think I want to do some, I want to run a great compute shader. And I ask my accelerator view guy, hello, give me the command pool for a queue that can do my compute shader. And we'll see in just a bit how the actual selection goes for that. What? Oh, I didn't put it. That's so sad. Oh, later on. Now, that was the interface. You might observe that I'm using CRTP for the interface. I'm not dogmatic about this. It's just personal preference. I wouldn't like to delve into it. This is the actual implementation. And is anybody here a DoD fan? DoD? Is it Department of Defense? No. There was a guy at the first CppCon that gave a big talk about it with a Hawaiian shirt, red, Mike Acton, data-oriented design, data overall. I'm not going there, but let's start with the data. So in the actual implementation, you keep a back pointer to the device that you're coming from. Why? Because there are cases in which you need to efficiently be able to query the physical device that you're layered on. For example, to see, well, what kind of extensions do you support? For example, is there any particular data member that seems freaky or that needs clarification? These are extensions that are device extensions. The other ones were extensions. Those are indeed static. The question is good because there is, if you remember, there was an accelerator pool type, and that actually offers a rapid query into the set of extensions that a physical device supports. And my answer to this question is that I was lazy. It might be. So instead of this, it might be a call into that. I'm not dogmatic. Anything else? If you look at the bottom, that pairing between the command pool and the queue that I mentioned is sort of apparent. They're literally a pair. And this is how you pick. And sorry for the bit flipping. It was late last evening. I literally added this last evening. This is how you select a particular queue family. Because within each family, which is to say within each doorway towards execution, you can have multiple queues against which you can submit packets of the same type. So it is a bit, maybe it is a bit daunting initially, but it kind of makes sense afterwards. And all of these are queryable. And the basic idea is that Again, the spec guarantees that you will get the universal queue, which probably will have everything that you need. That will match everything. So if you have no other queue that can take your work, you'll get the universal queue and it will be fine. However, I would like to get the queue that actually has the least facilities enabled but can still support my kind of computation, which is precisely what this does. And there are some other invariants here that you will pick up from the standard if you ever parse it. These indices, because they kind of sort of appear to be indices into arrays that exist in the driver, these mappings have to be maintained. So if when you do your query, a particular queue family has index 0, that will forever be index 0. So if you sort your stuff and you don't store that particular index, you might be a bit unhappy because you have to pass the queue family index into various structures and functions later on. So better just the order in which you grab them is fine. By the way, there aren't that many potential queue families to begin with anyway. There is a hard upper bound on them. It's 2 at 4 minus 2 probably, so it's roughly 14. 0, 0. So there are 4 bits which control the capability of a queue. It can be a compute queue, it can be a graphics queue, it can be a transfer queue or a sparse queue. And the sparse part is about SVT sort of applications. I'm not going to talk about it today. But the basic idea is that you have 4 bytes, 2 at 4. 0, 0, 0 is not a valid pattern. A queue that is only sparse is also not valid because you can't do anything with it. Transfer queues are specialized for transfers. You cannot submit computation or any sort of other request, but if you need to move a buffer from somewhere to somewhere else, either on device or from the host to the device, they're probably the best candidates, and so on. And this is how we actually build them. All the query stuff that we've been talking about. So bottoms, you will observe that there are a bunch of helpers. We're going to see make device in a bit. There are a bunch of helpers for making all of these types because there is a recurring pattern around making a particular Vulkan type. You usually fill out a structure, call a function, and return the handle that it retrieves. So it makes sense to automate that into a single because otherwise it's kind of difficult to put things in constructors. Now, what you'll see here with the static struct is a bit of a hack. The role of that particular part is, technically you can associate, let us say that you retrieve a family of queues that are capable of compute. You can associate priorities with the queues that are part of this family. So let's say that I have 3 guys. I can say that the first guy is 1.0, highest priority. The other guy is 0.5 and 0.1. And maybe the runtime will do something with this, and maybe it will honor it, but the spec says maybe it will honor it or not. I guess it is probably useful for someone. I don't know for whom. I just make them equal, and we're going to have our own sort of self-balancing mechanism a bit later on. So that work is kind of not utterly unfair. It's not smashing against a single sort of queue. And it's pretty safe that no device is going to expose anytime soon more than 64 queues. You don't need anything more than 640 kilobytes, right? So doing it like this, it just needs to exist as your instantiating. Basically, it's an op, it's filler. I need it in order to create the queue, but that's where it stops. It's not useful for our context. And now we can actually do something that is moderately more interesting, which is data movement. And does anyone have an issue with the idea that there might exist a particular memory space that is kind of opaque and owned by a device that is disjointed from you and that needs special massaging to be accessed? it's kind of a bit alien theoretically. If you start from the C machine model and so on, you expect that you can run through all of the. However, device memory can be theoretically physically located on a device and can be definitely in that situation not seamlessly accessed. You can't take a pointer and reference in there or whatever. It's opaque and it's a procedure to retrieve it. I'll get into that as well. This sort of changes for machines such as you might have on your phone or with modern SoC machines which actually have shared page tables and actually might see a flat memory space. But that's what the fast shared memory option might map to. And we're interested in these three in particular because the accelerator memory, which is to say the one that is on device, can potentially be massively faster than the alternatives. And by massively faster, we have GPUs that have 512 gigabytes per second in terms of throughput, HBM, good stuff. There's even, I think that the new Teslas have even more than that, maybe. That's a lot, but it's for memory that is local to the device. Whereas if you have this device that plugs into PCIe or into some socket somewhere, and you're forcing it to put it into a space that is shared, which is a pinned area into main RAM, blah, 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 you're going to be bound to maybe 15 gigabytes, ignoring the latency of the transfer, maybe 80. We're talking an order of magnitude difference. That's something useful to have. The fast shared memory bit, which is quite common, at least as far as Vulkan is concerned, on SoCs. So, for example, that machine actually has, that's an AMD thing or another, is theoretically equal speed access from the device and from the host. The non-fast one is actually slower from the device because it needs it needs an extra map, and just host the device cannot see it. But it might be faster for the host itself because it might cache it. So as things are now, again, due to what I mentioned earlier about how this whole shared memory space madness works out, you either get the fast shared space, but the host cannot cache it. So if you do a load or if you do a write, you always go to memory. Or you have a portion of the normal memory that is properly cached by your CPU, but that is not shared with the GPU because the GPU cannot snoop the caches of the CPU. And this is a simple way to maintain coherency. Now, we spoke about, does everybody know what swizzling is in context? Does anyone not know what swizzling is in context? So the basic idea is that within a texture, you might have the data rearranged in blocks that follow something like a Morton curve, or it's proprietary to each GPU maker due to the fact that when you actually fetch from a texture, you might want to do something like bilinear filtering or maybe trilinear filtering, and the texture units are optimized for these particular fetch patterns as opposed to bang, 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 because you might need 2 lines or something like that. Both types, so in Vulkan there exist linear textures, which are what you would expect, sort of row major, byte, 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 and the swizzle guys. There are restrictions on the swizzle guys. They might be faster on certain machines, obviously, but the linear guys you can sort of almost use directly. And we're all buffers anyway. This is the syntax for getting a buffer. You tell its type. Those are just the funky things that are constructed in place. They're just tags. They return a particular bitwise combination that is used deeper down in the maker functions and so on. It's nothing particularly fancy. There are multiple. The generic buffer is what you would expect it to be. The special cases tend to be tied to graphics rendering more than anything. So vertex buffers, index buffers, uniform buffers, which are also known as constant buffers, and so on and so forth. But you can create all of them via the same mechanism. there exists also a constructor here that that is not listed and that does not take an accelerator view argument, which is useful for the case in which you have a bunch of data. You want to stick it in there. You want to use the buffer interface, but you might not have the accelerator view ready yet. Also, note that these can be the declaration of this particular handle to memory and the binding to the actual backing memory is decoupled in Vulkan. So you have to call a particular bind function at some point, and at that point, your buffer actually has its backing memory. So another usage scenario, it doesn't apply here because I bind it at construction, but in general, another usage scenario would be you spawn all of these buffers and then you bind memory to them later on. And we'll see one case when it can be actually quite useful. Can anybody see an issue with creating the buffers like this?
What's stuff again? I'm sorry.
Pardon?
I didn't follow what.
It's the number of elements, the number of T's that you put in the buffer.
The T pointer is.
It's a pointer to that many T's. So it's akin to having the vector. Does vector have an initializer with size and data pointer, or is it pair of iterators always? I forget. Does anybody see an issue with doing buffers like this? Because there is an issue with certain types of buffers if done like this. So if I start allocating 3 integers, 4 integers, 5 integers, 1 integer, 2 integer, and so on, I get a bunch of really tiny thingamybobs. And this sort of syntax allows it. It's just fine. It's a performance anti-pattern. So if you're always allocating buffers of hundreds of megabytes, it's fine. Probably will not feel it. But for all of these small buffers, there is an overhead with having to trace so many handles and to grab them and to position them somewhere in the. So a strategy to employ here is to go with pre-allocating a larger buffer in a particular memory space and treating that as a heap in which you put all of these small guys. Because there is a syntax in which you can index into a larger buffer just by offset, into a larger memory allocation and offset into it. I mention this because you will read presentations that will get very angry when people just allocate lots of small buffers. So making people angry is not nice.
Do you have a buffer view class here then?
Pardon?
Do you have a non-owning buffer view?
No. I considered it, I just did not implement it. It's useful. I didn't implement it at this point. Because it also steals a bit of the functionality from that. The buffer itself, it is owning, but it also has information about its size and its location and so on, which is part of what buffer view gives you in Vulkan. Now, the process of mapping is taking some pointer to memory that is on the device and putting it in a place where the host can see it, where host is the CPU. And this is all beans. It's been in graphics API since forever. But again, if you map it, you also have to unmap it at some point. So area is your friend. So let's do it like that. Why is it not just a pointer? Well, because there are alignment restrictions on the sort of pointer that you can put your mapped pointer into. And I know this sounds interesting, but it actually is. Device dependent. So for example, on AMD machines, it has to be 64-byte aligned, the address of the pointer that you're writing into. I think on NVIDIA machines, it was 256 at some point. This is queryable, but that's the reason for having all of this stuff, just so that I can do align. And once you have this guy, you can do something like this. Which is pretty nice. You just map into a scope and you don't leave it mapped forever or dangling because you can't. I mean, I think it's nice. And at that point, as I said, you have a point, you can treat it as a pointer, as a normal any pointer, and you can do whatever you'd like to do with a normal pointer. Now, because I saw an interesting, I'm going to sort of skip over this. Will you take my word that I can copy and we can copy data from accelerator to device and device to accelerator and so on? And there will be proof of existence. It's not, it's interesting, but it's not massively fancy. But let's at least get to do some compute. This is a command buffer. This is the way in which you talk to the machine. But you'll see that as well. So I want to sort in parallel, and we don't have much time, and you're experts. Give me an algorithm that we can sort of discuss and implement rapidly. This is a widely parallel machine. What? It's hard. Pardon? That's also hard. You guys have no mercy. I mean, please give me something easier. Could you do a merge sort? I mean, merge sort in parallel is an interesting problem, but it's tricky to do well. Radix, something simpler. Bitonic is a good idea, and it's pretty simple, but it has one flaw, which is that it is not adaptive in any sense. And it has nice runtime characteristics, but you always go n log square of n. It's because the network itself is incomplete, you're only guaranteed to have sorted when. So simpler than that, not as good as that in the worst case, but potentially better if you have data that is already sorted. What's the simplest sorting algorithm that you do on the single-threaded CPU, something?
Bubble sort.
Yes! Now, you will be amazed that there exists something called odd-even potentially transposition, but odd-even sort. That's 1971 Haberman for parallel machines that can actually be potentially be sort of useful. So it's not as bad as bubble sort, assuming a series of properties for your exchange, but it's really simple to implement. And now, GL people will know what this is. People who are not GL, this is just blah. No, really, it is. I mean, GLSL, it's not my fault. And this is actually how we do the sorting. So again, funky syntax. Kind of not my fault. I would have liked to do it Socratically and start with the most stupid and to arrive at this, which is not the greatest, but is not the stupidest, but I couldn't. Are there any particular questions about this implementation? Yeah, just that it works in parallel. It's the same. So if you look at the network, it's odd, even, odd, even, odd, even, which bubble sort just does on level of. But, pardon?
I don't know about other people, but I have it difficulty following what this thing is doing.
Right, okay. So, the TIDX thing is your position in the globe. So assume that you have n elements. These elements are processed in chunks of group size something something. There was an odd prefix on top of. Do you know how GPU can? Okay, so you know about wavefronts, warps, and so on. So you process these in work group size. That's the OpenCL term, if it's fine, right? So this would be the starting address for the chunk that is going to be processed by the wavefront, the TIDX. The LIDX is the address within the wavefront, so it's basically the sim delay in index. And the GIDX is actually putting you twice within the chunk that you're processing, because each chunk is actually twice the work group size. Why? So that I don't need to mask, except if you're at the tail, which happens at the bottom. So it's 0 maps to 0, 1 maps to 2, 2 maps to 4, and so on and so forth. and it goes two sides. And the compare exchange thing does exactly what it says. So it looks at if they are out of order, which is to say if y is less than x, it swaps them and it returns a bool. It says I swapped something, and that way I can follow. The atomic add is there because I don't want to do atomic adds against an address that is in global memory. I don't want to do a ton of that because that's expensive. So that particular variable is in shared memory. So whenever a guy actually has to swap, it increments it. If it is actually positive, it means that I had some swaps. And only then is just one write per work group to global memory. That's why the Socratic method would have been good, but I posit that we can do it like this, where that literal is exactly the main that you saw from before, and just the main without all of the blah. And now, since there is not much time, are there any, do I go on, or are there questions that you would like to ask? That's very good. So the question is, does Vulkan use GLSL, which was the OpenGL shading language, or how do you write shaders in Vulkan? And the answer is that there is no particular orthodox way that is mandated by Chronos. They provide SPIR-V, which is sort of an intermediate language, and some SPIR-V is supposed to be really great, but I think that they only did the research on compiler front ends. It's really great for that. It's not so great for humans. So it is possible to actually consume GLSL either via proprietary extension from NVIDIA, where it just works in line, or as I do it here via shader-C. Shader-C is a library provided by Google. It consumes GLSL. It gives you the SPIR-V. Vulkan itself, without the extension, only knows how to talk with SPIR-V. So when you create a VK shader module something, you have to give it SPIR-V. Thank you. Anybody else? No? Do you want to finish the sort? I don't think that there's time there. There are 2 minutes. So in 2 minutes, I can explain how this automagically actually works, just with this funky syntax. The pipeline constructor itself, you'll see that it's kind of a soup of things. And if we go back to, if you look here, A, B, and C, those are names that are actually present in that shader hypothetically. And what happens in the constructor is that it goes, and it goes through its argument list. And let's say it sees a buffer, actually that strange pair of buffer and the string that gives it a name. It's going to insert it into a particular set of buffers that it needs to add to a descriptor set at the end when it is actually in a position to build a pipeline and the shader. And it's going to assign to it a unique binding point, which is this is serial, so it's sort of easy. So you just have a counter per category. I see a buffer, it's bind point 0. I see another bind point 1, and so on. There is such a concept of binding points within GLSL, and which we can precisely map these kinds of structures into the shader. It goes and sees a texture, not for the compute part, but if it were, not for this case, but if it were to see a texture, it would give it a unique binding into the set of textures and so on. Now, if it sees a constant that is a trivial type, and actually the restriction is kind of stronger because not all trivial types that exist in C++ can be split into a shader. For example, you can't put a pointer. It's not going to put it into a buffer or anything of the sort. It's going to put it into the funky called push constant space. And this is, you can think of it as a contiguous range of bytes in which you can put stuff at various indices that are determined by. And the way in which it works within the constructor is that it sees an integer. And it gets the unique index for that particular integer, and it updates it. Multiplies the index by the size, updates it, and so on. Which I didn't say right. It tracks the last, the position in which it should write. So I write 4 bytes, I update where I should write the next, I write 8 bytes, and so on. So all of this stuff should actually be done in a pretty nice front end, as opposed to being done manually. The ideal syntax for this is, well, one of the better syntaxes for these is to use the lambda capture part, but you actually need to do work on the compiler front end. And you could just capture the buffer guys, and magic happens in the background, and they are put into your shader at the right point with their program name without you having to repeat it, which is what C++M did. Now, having said this, my wonderful colleague is despairing that the session is over. So thank you for coming. We didn't get as far as I hoped we would. I'm sorry about that. I didn't kill 10 people, so it's fine. It's under 10. If there are any other questions, I'm here. So thank you very much.